Good afternoon, everyone. I hope I'm audible. Good afternoon, everyone.
Hello, can you hear me?
Yes, sir. We can hear you.
All right. So I'm ready whenever you guys are ready, okay?
Yes. Good afternoon, everyone. It is my honor to introduce our next speaker, Dr. Krishna R Reddy, eminent university scholar, distinguished researcher, and professor of civil and environmental engineering, the director of Sustainable Engineering Research Laboratory, and also the director of Geotechnical and Geo-environmental Engineering Laboratory at the University of Illinois, Chicago, USA. Sir has received his PhD in civil engineering from Illinois Institute of Technology. He is also a gold medalist from IIT Roorkee and Osmania University, Hyderabad during his MS and BE degrees. Dr. Reddy has over 25 years of rich research and research teaching and consulting experience in the field of civil, geotechnical, materials, environmental, sustainable, and resilient engineering. His research expertise and research interests includes environmental remediation of soils, sediments, groundwater and stormwater, solids and hazardous waste management and landfill engineering, engineering applications of waste or recycled materials, life cycle assessment and sustainable resilient engineering, geotechnical engineering. His research is funded by federal, state, and local government agencies and industries. He has also authored major books on sustainable engineering, geo-environmental engineering, electrochemical remediation technologies for polluted soils, sediments, and groundwater, and sustainable remediation to contaminated sites. He is also author of 246 journal papers with an H-index of 62, 21 edited books or conference proceedings, 22 book chapters, and 224 full conference papers. Dr. Reddy has given over 200 invited presentations in USA and 20 other countries. Dr. Reddy has received several awards for excellence in research and teaching, including the ASE Wesley W. Horner Award, ASTM Hogan-Togler Award, UIC Distinguished Researcher Award, University of Illinois Scholar Award, and University of Illinois Award for Excellence in Teaching. He is a fellow of American Society of Civil Engineers, a diplomate of geotechnical engineering, and a board certified environmental engineer. He is also a registered professional civil engineer and an Envision sustainability professional. We heartily welcome you, sir, for the webinar. We are grateful to you for accepting our invitation and marking your presence here. Thank you, sir.
Yeah, thank you.
I now invite you to enlighten the participants with your rich experience. Over to you, sir.
Okay, thank you. Thank you so much for that long introduction. I hope you can hear me well and
yes,
you can see my screen. Is that okay?
Yes, sir. We can see your screen as well.
Is there anything? Let me see. Okay. All right. Just, okay. So again, I want to thank organizers for giving me this opportunity to present. I'm going to present on geo-environmental engineering. I don't know how many of you are familiar with this topic. Hopefully my presentation can give you some ideas on this. So I understand, we have students and some faculty and some industry people joining. So I'm not going to go into a lot of technical details, but I'm just going to give a broad overview to geo-environmental engineering and the importance of addressing the sustainability in this field, okay? So as pointed out, I am from University of Illinois at Chicago. And I always show the picture of Chicago. So this is where the map of the USA and the Chicago, where it is located compared to New York and LA and all the places that you are familiar with. So Chicago is a beautiful place. Highly recommend you to visit. If some participants have visited Chicago, they can agree with me. But if you are new and if you plan to visit anytime to US, please get in contact with me. I'll be very happy to show you, and especially for civil engineering, Chicago is a model city in terms of building the infrastructure, at the same time maintaining the quality of the environment. So before I get into my presentation, I want to give you some background about myself. As I mentioned, I'm from University of Illinois, and I am in charge of these two labs, Sustainable Engineering Research Lab and Geotechnical and Geo-environmental Engineering Lab. My research is mostly on environmental remediation of soils, sediments, groundwater, and stormwater. And then I also work on waste management and landfill engineering. That includes beneficial use of waste materials, landfills, those kind of things. And then for the past few years, I've been working on life cycle assessment and sustainable and resilient engineering. Here, I'm more focused on developing assessment frameworks that can be applied in any engineering field. So in my case, I applied the sustainability assessment frameworks to assess the sustainable infrastructure, waste management systems, remediation systems, and so forth. So it has a very broad applications. And then my background is geotechnical engineering. My master's and PhD were in geotechnical engineering, but my bachelor's, as many of you, is in civil engineering with the structural engineering as a specialization. But these first two topics you see, the environmental remediation and the waste management and landfill engineering, those come under the subject of geo-environmental engineering. Whereas this third one, life cycle assessment, sustainable and resilient engineering, is kind of a very broad. It's a sustainable and resilient engineering that has become a very hot topic these days. So whatever we have done over the past 25 years, all of that has been summarized in these 4 books and many journal papers and conference papers. I highly recommend you to go to my website, and you will be able to find more information on our publications. So I just want to give you a little bit about my research philosophy. We identify a real world problem. What is the problem that is there? And we try to come up with a hypothesis for a solution. And then we try to test our hypothesis through bench scale testing in the lab. And if we find success, then we will scale up, again, do the testing in the lab, because it's easy to do testing in the lab compared to doing anything in the field, because in the lab, we can systematically control the variables, and you can understand the fundamentals. And again, in the large scale testing, if we find it feasible, then again, we try to understand the fundamentals, and then we incorporate all these fundamentals into mathematical modeling. And mathematical modeling is a way to scale up what you have done in the lab to field scale scenario. So we do the mathematical modeling. Through modeling, we scale up and design the field systems. And in the field systems, we first want to test if it works or not. So we do a small scale field pilot scale testing. We go out to the field and do small scale testing in a small area and see what we came up with is feasible or not. So if it works out in the field, then we develop design recommendations for practitioners to use and implement those solutions. So we follow this systematic approach in all the projects that we work on. We are in a university, so our duty is to advance the fundamentals, but we have obligation to the society to solve the real world problem. So I always say that we are advancing the fundamentals. At the same time, we are trying to develop a very practical solution to the real world problems. So I do a lot of experimental research. This is my lab. We have a soil and material testing equipment, geochemical characterization equipment, geochemical testing equipment, and the bench scale testing. Depending upon the project, we create small scale models, and for small scale or large scale lab testing, we use these things. So over the last 25 years, I have a privilege of working with research students and scholars from all over the world. In US, we get students from all over the world. So it's very nice to work with these talented students. Not only, we work together on technical issues, but it's very enriching to interact with culturally diverse research group. We talk about the language, we talk about the food, we talk about the social activities and families. So it's a very enriching environment. I always tell people that I have the best job in the world, not only because of doing the interesting stuff, technical on technical matters, but also in terms of interacting with these research students and scholars. So I really enrich my understanding of society and cultural aspects through these interactions. So let's come back to the presentation. So in the presentation, as I said, I want to just give you brief introduction to the geo-environmental problems. And then I'm going to explain some of the geo-environmental engineering solutions that we have. And then going forward, we need to be thinking about geo-environmental engineering solutions that are sustainable. So now the question is, how do you say an engineering solution is sustainable? So how do we quantify the sustainability? I'm going to show this through two examples so that you can understand this. Not only in the geo-environmental engineering field, but this kind of assessment is needed in any engineering field. If you are working in a different area, whatever I'm going to talk about, that could be applied, in your area of interest too. Then at the end, I would not say conclusions, but I would say, take a message that you can from this presentation. So let's talk about geo-environmental problems. So there are many geo-environmental problems. One of them is the garbage or municipal solid waste. Many participants are from India, and in India, you don't have proper engineered landfills. So you have mostly dump sites, and dump sites, can create a lot of problems. You have air emissions, water pollution problems, and the land contamination. You hear in the news all the time that a landfill is on fire and it's emitting all kinds of gases. And that is obvious, you can see it, but a lot of things that you don't see are leachate infiltration into the subsurface or into the surrounding water bodies, contaminating the waters, and also, contaminating the land surrounding it. So a lot of, health issues and damage to environment as a result of these uncontrolled waste dumps. So you also have a lot of industries generating a lot of hazardous waste, and you wonder, what they're doing with these waste. So not everything is recyclable, and eventually some of these things have to be, they have to get rid of it. And a lot of times, these things are thrown indiscriminately. And again, you have a lot of toxic substances that enter into the ground and into the groundwater, or through surface runoff, it could enter into the surface waters. So it's a huge problem with these hazardous waste issues. Then you have a nuclear waste. Nuclear energy is considered as zero greenhouse gases, and it's considered to be clean energy. But the biggest problem with the nuclear energy is the creation of this nuclear waste, and this is going to persist for many years. So what do you do with these things? So a lot of times we contain this one, and the containment facilities for this highly toxic nuclear waste have to be much more stringent than hazardous waste or municipal solid waste. So what kind of containment systems that we have to have for nuclear waste, that's a huge problem. The mine waste, India has a lot of mines, and many other countries have mines. The bad part of mining industry is that you recover the resources that you want, but then you create a lot of waste. The mine tailings and whatnot, other types of liquids that are generated, process liquids that are generated. And how do you handle those things? A lot of times you see that, they are not handled properly. So, if you have some kind of, physical damage to containment facilities, you have release of all the toxic substances. And if you don't have a liner systems at the bottom and all those things, then a lot of this contamination is entering into the subsurface and causing a lot of problems. So, and even related to power plants, coal-based power plants. In India, we have a lot of coal-based power plants, and many countries have it. Now, because of the climate issues, many of them are closing. But one of the byproduct of this coal power industry is coal combustion residuals like fly ash, bottom ash, FGDS, and those kind of things. And a lot of times they are mixed with water and pumped to impoundments, and the impoundments are not lined. So a lot of things leak into the ground, a lot of discharge into the surface waters, and a lot of problems associated with these things. So there are new government regulations came into existence in US. So now you need to have a containment systems, and all the problems that were caused needs to be fixed. So it's a huge problem to deal with. So as you know, a lot of industrial waste, right? Steel slag, carbon lime, asphalt waste, fly ash, slag, all kinds of these things are being produced in enormous amounts all over the world, even including India. So what do you do with these things? So they are being, stockpiled or indiscriminately, stored, at the plant sites. I see a lot of people, trying to use these materials as a construction material. And you need to be careful from geo-environmental perspective. You need to see if they are environmentally friendly to use it or not. A lot of times people do, physical, and strength testing, those kind of things, mechanical testing. But you need to look at, leachability and any kind of toxic substances release from these materials. So reuse of these materials is great as long as you're not causing any environmental issues with this thing. So there's a large problem with the use of industrial waste and not causing any environmental problems. So then you have polluted sites. I have shown these pictures. At some of the sites you can see at the surface, what is wrong in terms of the contamination. But a lot of sites you don't see anything. Everything looks normal, but maybe somebody buried something underground, or there was some accidental leakage or spillage. So soils and groundwater at that site could be contaminated, and that can pose a lot of problems. If the contamination goes into the groundwater, and you could be drawing the contaminated groundwater, drinking it, and you could get a lot of diseases out of that. And even contamination spreading, or contamination in the soil. If you grow any crops on contaminated soil, contamination is going to be uptaken by the plants. It could contaminate the food chain, and as a result, people can be adversely affected in terms of the health. So there are a lot of issues with the polluted sites. And then recently we are looking at climate impacts. You probably have seen or heard about greenhouse gases, climate impacts, extreme hazards that are happening. A lot of some places you have extreme flooding, some places extreme drought. All kinds of these weird climate impacts are being faced. And as a result, a lot of things that were designed in the past, they didn't consider these impacts. They never designed for this kind of flooding situation, or heavy storm events, or in the coastal area sea level rise, or surge protection, surge rise. So we have now dealing with a lot of these issues. Again, designing these containment systems in order to incorporate these extreme hazards. That's a huge challenge that people are facing. So those are all the geo-environmental problems. I call it, you could call this environmental problems, or but I call it geo-environmental problems because all of them have to do something with the soil, groundwater. So anything that is related to geomaterials, I want to call it as a geo-environmental problems. So now, these problems have been there for a while, and engineers, especially geo-environmental engineers, are working on different solutions. A lot of advancements have been made by geo-environmental engineers. So before I talk about those solutions, what is this geo-environmental engineering? Some of you may be hearing the term first time. So the geo-environmental engineering is nothing but the engineering that creates the solutions to the problems of geo-environmental problems, non-hazardous and hazardous waste management, characterization and mitigation of contaminated sites, and addressing the issues of environmental sustainability and resilience. So it's all about designing and applying engineering solutions to address these problems. Okay, so these solutions require some multidisciplinary technical approach. Just if you have geotechnical engineering background, you know soil and rock mechanics, but that's not enough. So you need some background on hydrology and hydrogeology, and you also need to have some background on geochemistry and biochemistry, and then you need to have some background on contaminant transport and transformation, and human and ecological health risks. So it's beyond geotechnical engineering. It's beyond even environmental engineering. So it's a combination of these two fields. That's what is geo-environmental engineering. So geo-environmental engineering is geotechnical engineering, environmental engineering, and groundwater engineering. So this field is also commonly known as environmental geotechnics, but in a broader sense, in a broader scope, it's called geo-environmental engineering. So instead of just talking about these three subjects, geotechnical engineering, environmental engineering, and groundwater engineering, now the geo-environmental engineering has evolved to be a truly multidisciplinary field. So for example, in geo-environmental engineering, we're going to look at environmental characterization, risk assessment, containment, remediation, waste management, or sustainability issues. And in order to address all these issues, you need to have a geotechnical background, environmental engineering background, environmental geochemistry, contaminant hydrogeology, environmental microbiology. All these things, the other things are needed. I'm showing all of them with the same size, but some of them, you need a lot. For example, geotechnical engineering, environmental engineering, scope is much more than, other things. So a lot of times the question arises, hey, how do I get so much of diverse background to work in geoenvironmental engineering? So it is, you don't have to be expert in all of them. This is where you need to work with your colleagues from environmental engineering. If you are a geotechnical engineer, or if you are an environmental engineer, you need to work with a geotechnical engineer. But we also need to, draw background from biogeochemistry, microbiology, and looking even environmental justice and economic issues, environmental laws. So you need to incorporate this broader background through collaborations. But these days, a lot of universities are offering multidisciplinary courses. So the students, that are studying now, they are getting a lot of these expertise from classrooms compared to, the time that I went to school. So if you want to get a little bit more background on how geoenvironment engineering has evolved over the years, so I recommend you to look at this article that I wrote in 2014, just to get an idea about how this whole field has evolved. So we have been working on this field for a while, and we have developed a lot of the solutions to the problems. So, for example, we have engineered waste containment systems, also called landfills. So we have developed the bottom liner systems, leachate collection systems, and the final cover systems. So this is the outcome of geoenvironmental engineers, and they are being used in US and other developed countries quite commonly, and we don't have any issues of waste management. We don't have any waste dumps. So waste is properly contained in the systems, and if you have a liquid waste, you have a surface impoundments with proper lining systems, and you have lagoons or ponds. They are all have liner systems so that soil or groundwater at the site are not contaminated. So these things are well established. And if the soil or groundwater is contaminated at a site, so what can we do to make sure that it is not going, it should not cause more damage? Then we need to have some engineered solutions. So these are called pollution containment systems or control systems, so like vertical barriers, like a slurry walls that we can build around the contaminated zones, make sure that contamination does not spread. So these technologies are also well established and are used very commonly. And then, at some sites, you put the capping system. So once the waste is filled up, or you want to, close a waste dump, one of the things that you can do is put an engineered cap on top of them, so that, you will avoid all kinds of problems associated with the exposed waste. So again, these capping systems are well designed, and a lot of work has been done, and many projects have used these cover systems. Then in terms of soil and groundwater remediation, there are many technologies that have been developed to remediate the soil or groundwater. There could be soil remediation technologies, groundwater remediation technologies. They could be in situ technologies or ex situ technologies. The technologies could be based on physical processes or chemical processes or thermal processes or electrical processes or biological processes. So based on all these factors, we have number of technologies. So what you have to do is you have to look at what are the site conditions that you have, soil and groundwater and contamination conditions that you have, and then you have to choose appropriate technology that best fits the site. So it is important for people working in this field to know all the available technologies so that they can pick the right technology depending upon the site that you have. And there is a lot of research going on these remediation technologies to further optimize it, make them more passive, less expensive. So a lot of work has been done is being done on these things. And there's a lot of researches, being done on pollution prevention. So, for example, source reduction. You don't want to have the contamination, to start with, and reuse of, the waste materials, and then recycling of the waste materials. So there is a lot of work going on. It's not about just, addressing the problem after it happens, but also looking at, aggressively upfront, not to cause the problems that needs to be addressed again in the future. So a lot of work is going on in this field. And recently, if you look at the literature, geoenvironmental engineers are playing major role on climate mitigation and adaptation. For example, growing the plants, for carbon sequestration. That's a huge area of research. And also underground carbon sequestration is a important topic, because if you have to immediately reduce the CO2 concentrations from atmosphere, this is one way, but there are a lot of challenges to that one. And also, not only trying to reduce the CO2 from the atmosphere, but also, we already have a lot of CO2 in the atmosphere, and we are seeing these extreme impacts. Then how do we address the extreme impact? So now people are looking at it, hey, how do we protect? For example, if I have a landfill right close to the coastal area, so that sea level is going to rise, or surge is going to be high. So how do we protect it? So now people are actively going back to the sites where some remediation has already happened, but they're retrofitting it because of this expected extreme events. So a lot of modeling work is also going on in terms of evaluating the existing systems for climate impacts. So this is a lot of work going on in this field. So if you are interested in geoenvironmental engineering, if you are just starting, you don't know much about this topic, I will highly recommend you to use this book. And I use this book to teach my geoenvironmental engineering classes at my university too. So we have these geoenvironmental engineering solutions, but the problem so far, and in fact, in other engineering fields is also true, that we didn't consider sustainability in developing the engineering solutions. Now the question is, many of you, I'm sure many of you heard about the term sustainability, right? These days, sustainability is the term that is used very commonly, whether one understands what it really means or not, right? Everybody is using it as a buzzword. And everybody uses this definition as the sustainability or sustainable development that meets the needs of the present without compromising the ability of future generations to meet their own needs. I like this definition. It's a very simple, very powerful. It conveys the message. What it is saying is that let's not do anything bad right now that can compromise the current generations and definitely compromise the future generations. So you wonder, when you say this definition, you ask yourself a question, are we doing something bad now that could affect us and future generations? So in fact, answer to that question is yes. Some of them are in our control, some of them are beyond our control. One of the biggest problems in terms of addressing the sustainability is the exploding population growth and consequent impacts. There's undoubtedly, the population has been growing exponentially. As the population grows, you're going to see all these problems, right? So you have a lot of demand for natural resources. So as a result, you are depleting the natural resources. Everybody wants to throw the stuff, right? So you have increased waste generation, increased pollution, damage to ecosystem, loss of biodiversity, urban sprawl, economic disparity, social injustice. All these things are happening just because of increased population. And there is not much that you can do in terms of the controlling the population. It's a very sensitive issue. So what is the other way that we can address these issues, realizing the fact that we are going to have a population growth no matter what. So that's where the engineer's role is becoming important. We cannot do things as usual. So we need to be very creative in addressing these issues. The other biggest problem is, this climate change issue. So CO2 emissions, greenhouse gas emissions are, uncontrolled, and we are seeing a lot of that in the atmosphere already. And as a result, we are seeing these extreme events. So there's a lot of push to control the greenhouse gases, because we already reached the tipping point where a lot of these impacts are impacting large group of population. For example, the flood events are happening. In India, many places, you never heard about these extreme floods. Some places it's droughts, wildfires. For example, in US, West Coast, California and other places, we never seen so many wildfires, and we are seeing all of those things. So these kind of impacts, they're going to generate now problems to the population now. And also, if we don't control the greenhouse gases, climate is going to get worse and worse. And in the future is going to be really difficult to deal with. So, we need to do something regarding these things, because we need to expect that these extreme events are happening, and how do we address those things in our engineering solutions. So I'm showing this graph, it conveys one important message. What I plotted here is, the year on x-axis and CO2 on, first y-axis, and population on second y-axis. As you see, population and CO2, they have a good correlation. So what it means is that even these greenhouse gases are increasing because of the population growth and doing the business as usual. So we need to have things, changed. Otherwise, future looks really bad. So, all of you, every engineering student and engineering professional have to understand that, UN, United Nations, has realized that sustainability is a big concern globally, and they developed this 2030 Sustainable Development Goals, SDGs, and many, students learn these things in schools or otherwise. And we have 17 goals with 169 targets, and they have been, started from January 1st, 2016. And one thing I want to mention is, I see people, picking up some of this stuff and then talking about them. But in fact, all of them are interlinked, some of them in a strong way, some of them in a weak way. But I don't like to see people, taking one SDG and saying that, oh yeah, we're going to work on this one. So because you have to look at the interlinking of, one SDGs to other SDGs. So I have given, some presentations on this one, how they are interlinked in the past. So no matter, who you are, whatever you can do, you have to start working on these things now. Now, if you are working in a geo-environmental engineering or as a civil engineer, you ask the question, what should we do specifically? So sustainability can be done, in different scales. You can contribute to sustainability through global scale, national scale, regional scale, business or institutional scale, or sustainable technology scale. Okay. So the global scale is like a UN. National scale is, the country is coming up with a policy. Regional scale, maybe the state, your state is coming up with a policy, or some area in your state is coming up with a policy. Business or institutional scale, a business or institutional, maybe your university can come up with a plan of, making your campus sustainable. The sustainable technology scale, last one, is the one where engineers can incorporate the sustainability in the things that they do on a daily basis. Sustainable materials, we use the materials for all our designs, right? All our projects. So why don't we think about, shifting our mind from conventional materials to more sustainable materials, more green materials, and the designs, and can we think about, conventional designs, can we alter them to make them more sustainable products, systems? So what I'm trying to say is, okay, don't worry about sustainability being a global problem, but you can do something at a local scale. As an engineer, you can do something that can overall contribute towards the global sustainability. So even if we, all of us do in our daily activities something, and then all of that efforts are going to add up and it's going to make a huge difference. So I would say that, everything that we do now, just ask yourself a question, is this sustainable? So keep in mind the sustainability question in your mind whenever you are making decisions. So the sustainable engineering is now a new field. What it is basically you have to design for the performance and the safety like we do conventional way. There's nothing wrong with that one. And we look at, the economic cost implications and, ease of construction. So the conventional approach is good, but we need to ask these triple bottom line aspects. So are there any broader environmental impacts of your project? What are the social impacts? What are the economic impacts? These are known as broader impacts of your project, and these needs to be addressed. And then we need to look at it. Engineers generally don't even think about this life cycle. So we need to start thinking about, okay, a lot of times we say, if I want to build a bridge, right? So we pick the materials, so you design a steel bridge or concrete bridge, and then we, give it to the contractor gets the materials and builds it. It's not like that. So when you are designing the sustainable designs, you need to look at, where the raw materials are going to come from, and then what it involves to make those construction materials, like, for example, manufacturing of the cement, manufacturing of the steel, or preparation of concrete. So you need to look at the impacts of that and the transportation of those materials to the site and the impacts of construction, and after that maintenance of the structure. And then we need to even think about whenever is the design life, 50 years, 100 years, whatever it is, at the end of life cycle, end of the life period, what are we going to do when we demolish that structure? How much of it can be recycled? How much needs to go to the landfill? So what we need to, when you talk about the sustainability in design, what we are talking about is making sure your design is meets the performance. For example, if I'm designing a column or for a structure, it should take the load that I have, right? That you cannot compromise. But what are the other impacts of this one? Maybe when you assess these impacts, you might find, hey, the solution that I'm using has a lot of impact, negative impacts. Maybe I should use some other thing, so you get those ideas and you can change things around to make your design more sustainable. So I recommend you to look at this book, Sustainable Engineering. We wrote this book mainly to give very practical perspective to sustainable engineering. How can we actually do something for sustainability? How do we design sustainable systems? I know, as I mentioned, there are a lot of talks, a lot of things, at the end of listening to those talks, and if you ask your question, what can I do with the stuff that I listen? So a lot of times you don't get anything out of those things. So this book is a practical way to do something in terms of sustainable designs. So this is the functional definition of sustainability. You saw that broad definition, Brundtland Commission definition, that's like a more philosophical definition. The functional definition is this triple bottom line. So you need to basically look at all the environmental impacts. So when I was talking about this, you need to look at the triple bottom line impacts. So the environmental is much broader. So you have to look at all these things. What is the greenhouse gas emission that's going to be from your project? Air pollution, energy, water usage, these kind of things. And we never talk about these things, right? Whenever we teach about structural design or foundation design, we never talk about these things. Now, everybody has to calculate these environmental impacts, no matter what you are designing. And then we need to look at the economic aspect. So this direct cost, materials, labor, transport, and equipment, that is an engineering cost estimate, that we are good at it. But we really need to look at indirect costs and benefits. So this is where you need to learn a little bit more about how to quantify these economic impacts. The social cost of carbon, social cost of health, employment opportunities. So there are different ways that you can monetize these impacts, and you need to take into account of this direct cost. So this is very important, and you need to look at a life cycle cost. Sometimes, the direct cost may be high, but there may be indirect benefits are much higher than that. So it's okay to spend more money, but the indirect benefits of this project are going to be much more. So you want to look at the holistically, what is the economic benefit of doing the project, not just the cost of construction. And the other aspect of triple bottom line, which is a very complex topic, is the social. So remember, some of the things that are happening in the society these days as a result of population growth. There is a lot of injustice issues, equality issues, discrimination issues, a lot of things that are happening. So you need to identify those social indicators. You as a person, how the project is going to impact, as a community, how it's going to impact, how the economic situation of the community is going to be impacting, how the environmental aspects of the community is going to be impacted. So engineers are not good at social aspects, but it is very important because all the projects that we are doing is for the societal benefit. How a society is going to get benefit out of your project. We need to take their feedback or at least analyze, the impact on them, with whatever the project that we are doing. So this is completely new to the engineers, but engineers are now forced to address these issues from the point of sustainability. So you need to look at environmental, economic, and social aspects. You need to have all these indicators because we are engineers. We believe in numbers. So all these indicators should be, can be represented in numerical forms. So they should have metrics, so-called metrics. So greenhouse gases, if you say, what is how many tons CO2 equivalent, air pollution, NOx, SOx, all those things can have a unit. So anything that you pick as an indicator, environmental, economic, all of the terms are in dollars, and social indicators, how do you, quantify the social indicators? So sometimes you use the surveys and use the rating as the metrics, but we need to have tools to calculate those metrics. So if you have indicators for environmental, economic, and social, and that have metrics, and if there is a way to calculate those metrics, then you can do the sustainability assessment, quantify the sustainability. But also remember that life cycle is very important. So you need to look at raw material acquisition, material manufacturing, transport, construction, operations and maintenance, all these things, as I mentioned, life cycle at the end of life. For each life cycle, you need to consider the triple bottom line. So you need to consider the environmental impacts, economic impact, and social impacts. So for each stage, you have all these impacts. Now you have this large list of environmental indicators, economic indicators, and social indicators. Now, how do I make a decision which one is more sustainable? So if you have alternatives, if I want to compare alternative 1, alternative 2, and alternative 3, and how can you say which one is more sustainable? So if there is a way to combine all these, several indicators and metrics into a sustainability index, that will be great, right? So if you have a one value at the end, let's call it sustainability indicator index, then based on that, you can evaluate different alternative designs and say the one which has the high sustainability index is the best option, right? So that's what we did it. Sustainability index can be calculated using this multi-criteria decision analysis. This is the framework that we developed. So you have indicators, criteria level, requirement levels, and you have those numbers, and you can apply the weighing factors if you want, because not all of them may be equally important. So you can make those considerations, and finally, you can calculate the sustainability index, okay? So you're using this multi-criteria decision analysis, and maybe you have to use the analytical hierarchy process to come up with the relative weighing factors. So there is a publication for more details on this one. I highly recommend you to go to my website and then download the paper that I have written on this one. So what I'm trying to say is you have to have this sustainability assessment framework so that you can assess whatever you have designed, is it sustainable or not sustainable? Otherwise, if you show me something and say, is it sustainable design? If you ask me, I might say, yeah, it's sustainable. And the second person might say, no, it's not sustainable. Third person may say it's not sustainable. So we can have an argument, but when you quantify the sustainability in terms of the numerical numbers, metrics, then there is no argument. So numbers will speak for themselves. So just let me demonstrate this approach with a case study, okay? So let's say in geo-environmental engineering, we deal with contaminated sediment. You have a lot of lakes, rivers, you have a sediment at the bottom that is polluted, and it's very important to clean up that pollution. That problem is there worldwide. I know you are dealing in India also, lakes, rivers, Ganga project, all those things you are dealing, because the sediment is a major concern. So this is the project that is in the US. So these are the ponds in that have been found to be contaminated. So if you look at these three ponds that I'm looking at it, close-up view of this ponds is this is the river that goes by, going back to here. This is the river that goes by, this is the river. But along the river, we have these lakes. So there are three small lakes. There's the North Lake, South Lake, and the West Lake. And these were created, and there's a railroad line that goes through across it. And these lakes served to supply the cooling water to a coal power plant that was right next to these lakes. And then, all the storm water, whenever it rains from the neighboring areas, all the water comes into these lakes. So as a result of all these activities, a lot of contamination entered into these lakes. The sediments are contaminated with pesticides, PCBs, PAHs, and metals. All of these are highly toxic if you get exposed to those things. So now, what they want to do is the coal plant is shut down. So, still that stormwater is going into this one, but they want to develop this as a nice park that people can use it. They can canoe and go with the families for picnic and other things. So they want to convert into a very nice park. But the problem is you have a contamination, sediments are contaminated. As a result, water is going to be contaminated, and you don't want to have children swimming in these lakes, right? So that's why the plan is, how do you clean up those sediments? So they did a lot of investigations from 1994. They collected the samples, they analyzed the chemicals. So the one that you see with the pink color, that shows that concentrations are exceeding the allowable limits. And they did sampling in 2017, and see that the pink colors have decreased. So only the pink colors you see here. So what is happening is, because the power plant is closed, and there is a little bit of control on the runoff that is coming into this one. So the contamination that is there in the sediments is naturally degrading it. So that's called that's natural attenuation. But there's some area that you see, this area, you see in the bottom right area, the contaminant concentrations are very high. So if they want to convert this one into a park right now, they have to clean up these sediments. Otherwise, you're not allowed to develop this as a park, recreational area. So this is the area that needs to be cleaned up. So what can we do? How can we clean up, right? So here are the, just looking at the site conditions, you can come up with the potential technologies. So these are the potential technologies. Monitored natural attenuation is called MNA, or other option is dredging and disposal. And there's a conventional capping and modified capping. Monitored natural attenuation is basically leave the sediment right there and then let it degrade. But degradation rate is so slow, that may not be acceptable. Dredging and disposal is dredging, taking out and then putting it in a landfill. And then conventional capping and modified capping is this way. Conventional capping is basically putting a cap on the top of the sediment. You have a sediment, so you put this multi-layered system on the top, you using the conventional soils, sand and gravel material here on the top. You have a multi-layered system. So this needs a very thick layer. The modified capping is, you have a reactive core mat on the top. It's more like a GCL. So you have a geotextile, and then you have a reactive material inside, and then you have a sand on the top, and then riprap on the top. So this is kind of, if you talk about engineering innovations, you're talking about innovative solutions. This modified capping is a innovative solution because we can put a reactive material inside here. As the contamination tries to diffuse from a sediment into the water, so the reactions happen. You're treating the contamination. Whereas in the conventional capping, there is no treatment. Basically, you are containing it. Here, you are containing it and treating. So if you are thinking about innovative solutions, you can think about modified capping as an innovative solution. And you have a lot of creativity in creating this reactive core mat or reactive layer in the system. So anyway, so now we have these 4 options, and you can come up with a preliminary design of these options. So, and then once you have the preliminary design, then I want to do this environmental, economic, and social sustainability assessment. So environmental sustainability, there's environmental indicators that I showed you before in terms of, the air pollution, greenhouse gas emissions, and so forth. Those can be quantified using, tools like LCA, life cycle assessment. And you have to have the data, the databases for this one, and the impact assessment methods for this one. So LCA is being taught now in civil engineering curriculum. People were not teaching this one, but now, a lot of universities, they are teaching the life cycle assessment, because this assessment can be used to assess the environmental sustainability of any engineering system. So if you do that kind of analysis, you get the results like this. These are the environmental impacts on the x-axis: ozone depletion, global warming, smog, acidification, eutrophication, carcinogens, non-carcinogens, respiratory effects, ecotoxicity, fossil fuel depletion. So these impacts, and these are shown often in a normalized manner so that one can easily understand it. So M&A, you don't even see anything. M&A is, you're not doing anything, so there are not going to be any impacts. But this first one, green is the dredging, and the red is the conventional capping, and the other one is the modified capping. You look at these things, so the smaller the bar size, better it is. So it's basically showing how much is the relative impacts. So as you see here, some cases, you see dredging comes out to be better. Some cases you have a modified capping, comes out to be better. So you need to look at it, relative impacts of this. And there are, many databases that you can use and assess these impacts. And then if you compare this, the conventional versus modified capping, so modified capping is much better than conventional capping in all environmental categories. And then you need to look at the economic sustainability. So how much is going to cost? Obviously, M&A costs very less. So, M&A, you're not doing anything, but you need to go and monitor. You need to collect the samples, so do the chemical analysis. That involves a lot of costs. And dredging and disposal, how much is the total cost? Conventional capping and modified capping. So you have here direct costs, and we have also included the social cost of carbon, and then we have the overall total cost of the project. Then we did a social sustainability assessment through survey. So basically you identify the stakeholders and you prepare a questionnaire and ask them to rate from 1 to 5. What do they think about this option? What do they think about this option? So you create a survey, how individually one is going to be affected, how the community is going to be affected, how their economy is going to be affected, and how environmental is going to be affected. And you look at the grant score. So here is the grant scores you can see, and public perception is quite different, so that needs to be accounted, because they're not looking from technical aspects, they're just looking in the general perception aspects. So now you combine all of the environmental, economic, and social aspects. And remember that framework I mentioned, you apply that one, you get a sustainability index. So M&A, monitoring natural attenuation, I got sustainability index of 0.6. And then next is modified capping, I got that index, and the conventional capping and dredging and disposal. So based on this final assessment, you can see M&A is the best choice, and the modified capping is the second best choice. But then you look at in the top here, if you give equal weightage to environmental, economic, and social aspects. Now, let's say I want to change this one. So environmental is not a big concern, economic is not a big concern, but social aspects is a big concern, because this project is going to be used by people. If you people don't, if you don't consider the people's impact, people's perceptions, then the project is not going to be successful. So if you give the high importance to the social aspects, this modified capping comes out to be higher one. So so that if you incorporate the social aspects, then modified capping may be the best option to go through. And if you look at maybe economics is the more controlling criteria, then M&A comes out to be better. So if you want environmental, then M&A comes out to be better. So you can see in all these three cases, M&A comes out better, but like if you consider the social aspects, then modified capping comes up to be better. So that's how we need to make a decision. So let me just run through this quick second case study. So let's say you have landfills or dump sites. You want to put a cover on the top of it to control the infiltration and also to control the gases. So this is the conventional cover system that we use. So you have a waste on the top, you have a gas distribution layer, compacted clay, drainage layer, and vegetative layer. What we are proposing is, instead of this, why don't we use this biogeochemical cover system? So this cover system is good for not allowing the infiltration of the precipitation, but it does not take care of the gases that comes out. Whereas this system, we proposing this system so that you can control the infiltration. Also, you can control the gas emissions. So the only difference is, instead of compacted clay, we are suggesting that the soil should be added, biochar should be added to the soil. And then instead of drainage layer, instead of being sand, we are looking at a steel slag. So this steel slag and biochar are the waste materials. So basically, using the waste materials is a good thing to do it. And you are improving the technical performance of this cover system. That's even more advantageous. So we have, this a huge project to work on this one. And we, try to understand the chemistry and biology, more fundamentals of this one through lab research. We do extensive lab experiments, controlling the different variables. As I said, we need that fundamental understanding of all the processes that happen, and then, as I said, just the lab research is not enough. You need to go out to the field and see what you came up, the optimized design that you came up through the lab research. Is it going to work in the field? Because you cannot simulate everything that happens in the field in lab, right? Especially the weather, environmental conditions, right? So for example, right now, it may be too hot, or sometimes it may be too cold. So you cannot, simulate those conditions in the lab. So it's very important to do some small scale testing in the field and then see if it works.
Can you hear me, sir?
So we're going to be, sustainability assessment, we need to do this one. And then, for example, we did for these two cover systems. And then, you see that one consistently, our new cover system can, address the greenhouse gases tremendously, because it's not allowing any greenhouse gas emissions. And then it also has other environmental benefits. So the point I'm trying to say is, now we are now creating new solutions, but we should not be just looking at improving the technical performance of the new solutions. We should also look at sustainability of the solution. So we need to look at this economic impacts, social impacts, and environmental impacts. So hope I'm trying to convey that message. No matter what you are doing, in terms of developing the new solutions, okay, for improving the technical performance, that's fine. But go beyond that, address the sustainability issues. So this is my last slide. I want to, take this message home with my presentation. So if you are working in geo-environmental area, there are many problems and we need innovative geo-environmental engineering solutions. They could be related to waste minimization, waste containment, polluted site remediation, climate mitigation. So there are many, many problems, this is a very exciting field and all of those problems need immediate attention. So we need to develop innovative solutions. There's no question about it, but not only, innovative, but also sustainable. And how can you check whether it is sustainable or not? We need to quantify the sustainability using that framework that I mentioned, triple bottom line and life cycle. Otherwise, you may say that it's sustainable, but you are just saying it without any evidence. So going path forward in our research, we look at innovative engineering solutions, we look at the sustainability, but now we are looking at the resiliency also, because we want to develop sustainable and resilient engineering solutions. And then we have actually developed a framework we call Tequilizer that integrates the sustainability and resiliency. We call it Sustainable Resiliency Index. We calculate that one. So if you are interested, I have some presentation on that one, and you can use that one for any engineering applications. So I have covered a lot of stuff, but there's a lot of information that you can get from these publications. And I just want to mention that last year, I organized a webinar series on every Friday. All the webinars are recorded. These are related to geo-environmental and sustainability. If you just Google geo-environmental engineering webinars, you should be able to end up with this YouTube channel. I highly recommend you to check out all the webinars. We have more than 60 webinars, and hopefully some of them would be very interesting to you. Okay, so these are given by well-known experts. I really appreciate going to that website, the YouTube channel, and check if anything is of interest to you. Okay, and other resources, contacting myself. So you can just contact me by email and look at my website and get more information on it. So I know I took a lot of time, but hopefully, my presentation is useful. If you have any questions, I will be happy to answer now, or you contact me. I will be happy to answer anytime in the future. So with that one, I want to pass on to the organizers for the.
Thank you for sharing your vast experience. Thank you for sharing your vast experience in dealing with geo-environmental problems and enlightening us, sir. Now the platform is open for Q&A, and also HOD sir would like to have a discussion with you along with that. Anybody has any questions? Only two people.
Sir, as you discussed about climate impacts and extreme hazards that mainly focused on flooding. So how can water work for cities instead of against it? So the global floods and extreme rainfall events have quadrupled since 1980s. And currently only 20 to 30% of rainwater infiltrates the ground in urban areas. So a solution that responds to urban high density challenges, especially a city like Mumbai, where we also have frequent weather events due to climate change.
Yeah, that's an important question. I mean, we have in Chicago is a big city, and even before climate, whenever it rains, it used to flood the streets and houses and so forth. So in Chicago, we built some underground tunnels to store that flood water, and so that the areas don't get flooded. But now with the climate change, expecting heavy precipitation, even those tunnels that we built, tunnels and reservoirs that we built, they're not going to be enough. So now there is emphasis on green infrastructure. So you need to have a green infrastructure so that water is allowed to infiltrate where it falls, and then have it ideally recharge the aquifer and avoid any runoff. So that would be the ideal solution. But in cities, you can do only so much. In some areas, you cannot do anything. So you need to collect that groundwater, the stormwater. A lot of urban stormwater is contaminated. You're looking at just the quantity of the water and flooding, right? But actually, on the roads, you will see a lot of oil and all the same kind of junk. So the water gets contaminated. So in Chicago, to address that urban stormwater that is contaminated, we created bioswales, and even some places we created reactive filters so that the contamination can also be addressed. So to answer your question, we need to go more and more into green infrastructure so that water gets infiltrated as much as possible. You're talking about permeable pavements, pavements for parking lots and so forth, and looking at the bioswales along the roadways. So all kinds of green infrastructure needs to be promoted to address the climate change impacts, and urban flooding. It's a very important thing to do it, and it's going on in many parts of the world.
Thank you.
Thank you, sir.
There's another question.
Good afternoon, sir. My question is that when you were discussing about the first case study in which you discussed about contaminated lake sediment remediation, there were many remediation alternatives like MNA, modified capping, and conventional capping, in which you showed many data. So basically, my question is that what is the accuracy or validation of that data of social sustainability assessment, because it is a ground survey data. So from that, how can we take the insights with related to accuracy?
So I don't know how, I mean, the accuracy of sustainability assessment is a little bit subjective. So a lot of times when you do the sustainability assessments, you are doing the relative comparison of the options, right? So you don't have to be extremely precise in terms of the numbers. Of course, life cycle assessment, the environmental sustainability, you have a good databases, good ways to calculate it, and it's more accurate. When it comes to economic sustainability assessment, again, direct cost is easy to calculate, that's very accurate. But when you go to indirect costs and benefits, there are some assumptions that are made, so that economic assessment makes it a little bit more approximate. When it comes to the social sustainability assessment, that's the extremely challenging task, because you are doing the surveys and it's a very subjective, and you're using the rating system. How you frame the questions, how you create the rating system, and so all those could be important. So I would say, I always get these comments, so social sustainability is hard to do it, but if you don't do it, how can you address the community issues? This sustainability is all about, making the difference to the people, right? So if you cannot really take into consideration of the people's issues, how can you do it? So my argument for social sustainability assessment is, it's not about the numbers, it is about the process that you follow, and that can lead to good solution. Because if you don't do the social sustainability assessment, you are not really assessing how the project is going to help the public that is going to be affected by the project. So even if it is approximate, going through the process of identifying the problems, identifying the potential benefits, that's the great benefit of doing the social sustainability assessment. So yeah, we need to all realize that social sustainability assessment is very subjective. There could be some variations, and that needs to be taken into account. Okay. But
Thank you,
also,
sir.
we are doing the relative comparison. So, and in relative comparison, how is one method, compares to other methods? We are not looking at the precise numbers for one particular method.
Thank you, sir.
Sure.
Thank you, Professor Krishna R Reddy. I'm very much glad to tell you that there's a lot of response. We appreciate the wonderful quality of the lecture you have delivered, voluminous information. In fact, we need a lot of time to digest it. So we appreciate and we compliment with our casual way of scrapping.
Thank you so much. Yeah.
Sir, I will take only fraction of a minute because the other speaker is already on the line. So myself and the principal of the institute would like to have some discussion with you with regarding to your program. Principal has as advised me. So after the session is over, I will call you from a personal phone to chat for some. Yeah,
Okay.
I will call you in 5-10 minutes, sir.
Okay. Yeah. Sounds good.
Thank you very much, sir.
Thanks, everyone. Thanks for your time. Bye, everyone.